Welcome to 3.2, Brute Force Notes and Practice. All right, so we talked last time about the optimal tour. And this helps us answer the question, how do I know which one is best? We've got all these different circuits. How can I know which one is best? I told you we had 3 methods that we were going to use. And today we're going to look at the first one, which is called brute force, also known as the exhaustive search. And it sounds like exactly what it is. You're going to do the same thing over and over and over again until you find every possible solution. The way that we do it is we make a list of all possible Hamilton circuits. And for each circuit in that list, we calculate the weight. From all the circuits then, you choose one with the least total weight, and that is the optimal tour. Now, it's called the brute force method, and it is very time consuming, but it is going to give you the optimal circuit or optimal tour. However, it is really inefficient, especially when you have a large number of vertices. Let's look. So Willie's graph has 5 vertices. So how many circuits would we have to check? Well, we know that in a complete graph, it's n minus 1 factorial to find the total number of Hamilton circuits. I put order here, just a little throwback to our past unit to remind you that the order of a graph is the number of vertices, but in your Kn complete graph, n minus 1 factorial is the total number of Hamilton circuits. However, when we do the brute force algorithm, we do not have to do calculations for mirror circuits because it's going to be the same number, the same root, just backwards. So to determine the number of unique circuits we'll have to check, we do n minus 1 factorial divided by 2. So here, if n is 5, 5 minus 1 is 4, and 4 factorial is 24. 24 divided by 2 is 12. That's 12 circuits that we would need to calculate their weight, and that's quite a bit, actually. If you look down here at table 6.5, you see all his possible tours. Here's the 12 unique ones and their mirror circuits. And we find that the Hamilton circuit that gives the optimal tour is the one with the lowest cost. And that's right here. It is $676 if we travel either from A to B to C to E to A, or from A to E to C to B to D, and then back to A. Now, wait a minute. What was that mirror stuff? Let's review. Look at the circuit that's been highlighted here. You can travel it 2 different ways, but you don't need to evaluate both because look at it. It's the same circuit with the same costs no matter which way you go. The mirror shows you the backwards reflection, and we call that opposite or backwards reflection the mirror circuit. All right, let's brute force something, but we're going to do something a little more manageable. All right. Here, we want to find all possible circuits starting from A. We want to find the weights of all possible circuits starting from A, and we want to find an optimal tour. Okay, well, we know that this is a K4 complete graph. So I know that I'm going to do 4 minus 1 factorial divided by 2 unique circuits. Now 4 minus 1 is 3. 3 times 2 times 1 is 6. So I'm just going to put that down here. I've got 3 factorial divided by 2. and that is going to equal 6 divided by 2. So really, I've only got to check 3 unique circuits. All right. Now, down here, it goes through all of those for you. We can go from A to B to C to D to A for 10 plus 6 plus 2 plus 4, which is 22. The mirror circuit going backwards is the same. Alrighty. We also have A to B to D to C to A, which is 10 plus 3 plus 2 plus 5, which is 20. And the mirror, ACDBA, is 20. All right. Now, to do the next one, I'm going to look. I've already used an A to D and an A to C, so I'm going to go A to C, but I've already used A, C, D in a mirror, so I'm going to go A, C, B, D, A. 5 plus 6 plus 3 plus 4 is 18, and the mirror, ADBCA, is also 18, and that is our optimal tour because it is our circuit with the lowest weight. Okay, let's do some practice. We're going to use the brute force algorithm to list all possible circuits from a point of our own choosing, list their weights, and then say what the optimal tour is. All right. Well, I'm kind of in luck for these two because I already know from here, these are the 3 circuits I'm going to have to check. ABCDA, ABDCA, and ACBDA. So, coming here, A, B, C, D, A is going to be 34 plus 39 plus 34 plus 30. Do that in my calculator. 137. All right. I can also go from A to B to D to C to A. Where am I going to put that? I'll put that down here. And that's going to be 34 plus, sorry, Major Tom just dropped his phone, plus 34 plus 33. So 34 plus 32 plus 34 plus 33. And that's 133. Our final circuit is going to go from A to C, but it's not going to go to D because that's the mirror of this one. So it's going to go to B, D, A. A, C, B, D, A. And that is 33 for A to C, 39 for C to B, 32 for B to D, and 30 for D to A. 33 plus 39 plus 32 plus 30 is 134. So this one here, ABDCA or ACDBA, is my optimal tour. Let's try B. I already know that I'm doing A, B, C, D, A. Let's look. A to B is 550. B to C is 270. E to D is 910. And D to A, goodness, 1,260. Adding that up, 550 plus 270 plus 910 plus 1260 is a total trip cost of 2,990. All right, next, A, B, D, C, A. AB is still 550. B to D is 670. D to C is 910. And C to A is 400. Going to add those together, and I get 2,530 as my weight for that circuit. Finally, we'll do A, C, B, D, A. So AC is 400, BB is 270, BD is 670, and DA is 1,260. Adding those up, 400, 270, 670, and 1,260 gives me a weight of 2,600. So then, here I have my optimal tour. Now, you don't have to start at A. You can start wherever you want. I just did that because it was a little easier to use the pattern from before. And I'll be traveling from Minneapolis to St. Louis to New Orleans to Chicago and then back to Minneapolis, or I'll be doing it in the reverse order. All right. Use this table to create a K4 complete graph and label the appropriate edges with their indicated weights. Then use the brute force algorithm with your graph to find all possible circuits starting from LAX, the weights of all possible circuits from LAX, and an optimal tour if we want to leave from LAX, visit the other 3 airports, and then come back. All right. So here I'm going to put Indianapolis, here RSW, here LAX, and here I'm going to put MSP. Now this is a K4 complete graph, so every single vertex must connect to every other vertex, which makes sense. If we're talking about airports and flying, I'm sure that I could fly from any one of these airports to any other airport directly. Now I need to fill in the weights. Starting at Indianapolis, to go to RSW is 253. To go from Indianapolis to LAX is 278. And to go from Indianapolis to MSP is 339. All right, from RSW, we've already gone to Indianapolis, to LAX is 222. And to MSP is 264. From LAX, I've already gone to Indianapolis and RSW, but to MSP is 248. And now you see I have all of the weights attached to the edges of my graph. So I'm now going to start looking for my tour. I'm going to start by going from Indianapolis, RSW, to LAX, to MSP, to Indianapolis. All right, I to R is 253, R to L is 222, L to M is 248, M to I is 339. So I'm going to add those together. And that's 1,062, which is also equal to IMLRI, which is the mirror circuit. Now, if I went to IRMLI, I to R is still 253, R to M is 264, M to L is 248, and L to I is 278. 264, 248, 278. That's 1,043, which is the same as it would cost to go I, L, M, R, I, which is the mirror circuit there. Last but not least, we'll go I, L. Now I cannot go I, L, M because that's a mirror circuit here that I've already done. So I will go I, L, R, M, I. I to L is 278. L to R is 222. R to M is 264. And M to I is 339. Add them up. 278 plus 222 plus 264 plus 339. That's 1,103. And that's going to be the same cost if I travel I, M, R, L, I. All right. So what is my optimal tour? Well, it's this one here because that one has the lowest weight. So I want to highlight that here on the graph. I, L, M, R, I, or I, R, M, L, I. All right. Good work. I will see you next time for section 3.3. Have a good one.